Welcome everyone to the final lecture in our unit on vibrational spectroscopy. Over the course of these lectures, we have traveled through an enormous range of concepts. We began with molecular vibrations, infrared absorption, Hooke's law, group frequencies, Frank condon transitions, FTIR instrumentation, and Raman scattering. We explored rotational spectra, vibrational spectra, polarizability, selection rules, and quantum mechanical transitions. Today, we bring all that theory together and step fully into the analytical laboratory. Today's lecture focuses on Raman instrumentation and sample handling and real-world applications. Before we discuss the actual instrument design, we need to remind ourselves one critical fact that Raman scattering is incredibly weak. Only about 1 photon in 10 million undergoes Raman scattering. This means Raman instruments must be extremely sensitive, highly stable, and optically precise. Even tiny background signals can overwhelm the Raman spectrum. Let us begin with the basic architecture. Every Raman spectrometer contains three essential components: a laser source, a sample illumination system, and a spectrometer with a detector. Each of these components plays a critical role. If any one of them performs poorly, the Raman spectrum becomes unusable. The laser is the heart of the Raman instrument. Unlike IR spectroscopy, which uses broad thermal sources, Raman spectroscopy requires monochromatic, coherent, and high intensity light. That means we need a laser. The laser provides photons of one precise wavelength. These photons interact with the molecular electron cloud and generate Raman scattering. Remember, Raman scattering is extremely weak if you used an ordinary lamp. The scattered signal would be buried in noise. The invention of the laser in the 1960s of what transformed Raman spectroscopy from laboratory curiosity into a practical analytical technique. Now let us look at the modern Raman spectrometer. You should immediately recognize something familiar in the optical diagram: the Michelson interferometer. Exactly the same principle we studied in FTIR spectroscopy. In FT Raman instrument, the interferometer modulates the scattered Raman light before the detection. Resulting interferogram is then mathematically processed using the Fourier transform. This provides several major advantages: high signal to noise ratio, excellent wavelength accuracy, and rapid data acquisition. Now, notice that the laser source. Modern FT Raman instruments commonly use Nd:YAG lasers operating at 1064 nanometers. Why this specific wavelength? Why not use a stronger visible laser? The answer brings us to the greatest enemy in Raman spectroscopy, that is fluorescence. Let us examine the problem carefully. Earlier, we learned that Raman intensity increases with the fourth power of frequency. Mathematically, I is proportional to nu raised to 4. This suggests we should use high frequency blue or ultraviolet lasers to maximize Raman intensity. And indeed, the visible lasers like argon laser 488 nanometers produce extremely strong Raman scattering. However, there is a major complication. High energy photons can excite real electronic transitions within a sample. This triggers fluorescence. The fluorescence is enormously brighter than the Raman scattering, often thousands or millions times brighter. If fluorescence occurs, it completely overwhelms the Raman scattering, Raman spectrum. The detector becomes flooded with fluorescent light, and the Raman peaks disappear into the background. This is especially problematic for organic molecules, biological samples, dyes, pigments, and polymers. The high energy lasers are introduced another danger: photo decomposition. The laser can literally burn, degrade, or chemically alter the sample. Biological materials are particularly sensitive. Even moderate laser powers can damage protein tissues or polymers. This is why Nd:YAG at 1064 nanometers was revolutionary, because the photon possesses lower energy and usually cannot excite electronic transition. Therefore, fluorescence is dramatically reduced or eliminated. This allows us increased laser power, improve signal quality, and preserve delicate samples. However, This introduces a trade-off. Lower frequency lasers produce weaker Raman signals. Remember, Raman intensity decreases strongly as the frequency decreases. So, Raman spectroscopy always balances two competing factors, signal strength versus fluorescence compression. Modern Raman systems commonly use 488 nanometer argon laser, 532 nanometer green laser, 633 nanometer helium neon laser, 785 nanometer diode laser, and 1064 Nd:YAG lasers. The ideal choice depends entirely on the sample. Now, let us discuss another enormous challenge, that is Rayleigh scattering. Remember, the Rayleigh scattering is elastic scattering. It is vastly stronger than the Raman scattering. In fact, maybe millions of times more intense. This means the detector receives the enormous flood of Rayleigh photons sitting directly beside the Raman signals. If you do not remove the Rayleigh line, the detector becomes effectively blinded. To solve this, modern Raman spectrometers use holographic notch filters. These are extraordinary notch optical filters designed to block exactly one wavelength, the laser wavelength. They act like an optical brick wall. They reject over 99.9% of the Rayleigh light while transmitting the shifted Raman wavelength. This allows the weak Raman signals to reach detector clearly. Now let us discuss the detector itself. Because Raman signals are weak, the detectors must possess extremely high sensitivity and very low noise. The modern instruments commonly use CCD detectors, charge coupled devices. These detectors provide high sensitivity, excellent dynamic range, and simultaneous detection across many wavelengths. For near IR Raman systems, special detectors are required because the photons have lower energy. Common choices include germanium detectors, indium gallium arsenide detectors, and cryogenically cooled semiconductor detectors. Cooling is essential because thermal noise can easily overwhelm weak signals. Now discuss one of the Raman spectroscope's greatest practical advantages, that is sample handling. So, compared with IR spectroscopy, Raman sample preparation is astonishingly simple. In IR spectroscopy, we needed salt plates, KBR pellets, moulds, or thin liquid walls, thin liquid cells. Glass cannot be used because glass strongly absorbs IR radiation. But Raman spectroscopy is completely different. Glass is mostly Raman inactive. That means we can analyze samples directly through ordinary glass containers. This is enormously important in real laboratories. You can analyze chemicals without opening the wire, without contaminating the sample, and without exposing yourself to hazardous compounds. Even more importantly, water is a weak Raman scatterer. This is one of the Raman spectroscopy's greatest advantages over IR spectroscopy. Water ruins IR spectra, but water barely interferes with Raman measurements. Because of this, Raman spectroscopy is ideal for studying living cells, proteins, DNA, biological tissues, and aqueous solutions. We can study biological systems in their natural environment without drying them, without destroying them, and often without any preparation at all. Raman spectroscopy is highly versatile for solid materials. Powders can be packed into glass capillaries, polymers can analyze directly, crystals can be examined microscopically, even microscopic particles can be analyzed using Raman spectroscopy. Modern Raman microscope combines optical microscopy with laser spectroscopy. This allows chemical mapping with micrometer scale spatial resolution. Scientists can literally create chemical images of surfaces and tissues. Portable Raman instruments have become especially important. Modern handheld systems can identify substances instantly in the field. This has revolutionized forensic science, pharmaceutical inspection, security screening, and environmental monitoring. Now, let us explore some of the major applications of Raman spectroscopy. Raman spectroscopy is exceptional for studying metal ligand vibrations, coordination, compounds, and inorganic ions in aqueous solutions. Many of these application systems are difficult or impossible to study using IR spectroscopy because of water interference. For organic chemists, Raman spectroscopy can provide detailed information about ring breathing modes, conjugated system, double bonds, and molecular symmetry. Raman and IR spectroscopy together provide a complete vibrational fingerprint of the molecule. In biology, Raman spectroscopy is used to study proteins, DNA, lipids, cells, tissues, and disease markers. Researchers are developing Raman technique for cancer diagnostic, live cell imaging, and medical biosensing. The pharmaceutical industry uses Raman spectroscopy for drug verification, polymorph identification, tablet analysis, and process monitoring. Because Raman spectroscopy can analyze materials directly through packaging, it is ideal for rapid quality control. In forensic science, portable Raman spectrometers allow investigators to identify narcotics, explosives, toxins, and hazardous chemicals without opening the container. The laser can analyze materials directly through plastic bags or glass bottles. This minimizes contamination and improves safety. Raman spectroscopy is a fundamental in modern nanotechnology. It is heavily used for studying graphene, carbon nanotubes, semiconductors, battery materials, and thin films. The famous G and 2D band in graphene research are Raman features. Environmental scientists use Raman spectroscopy to study pollutants, microplastic, water contaminants, and atmospheric particles. Over the course of this unit, we have journeyed from classical physics of vibrating spring all the way to quantum mechanics, Fourier transform, laser optics, and cryogenic detectors, and advanced molecular analysis. We explored how molecules stretch, bend, rotate, scatter light, and interact with electromagnetic radiation. We studied IR spectroscopy, Raman spectroscopy, Frank-Arnold principle, selection rules, instrumentation, and real-world analytical chemistry. This concludes our complete unit on vibrational spectroscopy. Thank you for your attention, your dedication, and your curiosity throughout this journey. I hope these lectures help to you spectroscopy not merely as a collection of equations and peaks, but as a powerful language that reveals the hidden motions and structures of the molecules themselves. Thank you, and I wish you all the best for your continued exploration of molecular spectroscopy. Thank you.